Chemistry 1, we learned about the ideal gas law. So we have lots of different gas laws which we don't focus on in this class because everything can be derived from the ideal gas law. So when you combine them all together, we get this number. Now, the reason why I gave you the equation sheet for reference is because you need to know which ones to use when you do this, okay? So the R in here is 0.08206 liters per atmosphere, liters times atmospheres per mole Kelvin. If you look on the page 13 side of the equation sheet, in the top half, those are where the pressure stuff is, okay? If you look there, there are three pressures, or three R's, excuse me. So you have to make sure that you're using the correct one. Now, from this R value, this tells us what the units will be for pressure, what the unit will be for liter or for volume, and what it will be for temperature. Okay? So this is why in Chem 1 this confuses you, so I leave it off. But in AP, you need to know which one to use, and it's based on the units that you're plugging in. Okay? So that tells us that pressure has to be in atmospheres, tells us that temperature has to be in Kelvin, and volume must be in liters when we use the equation. If you look on the equation sheet, it also tells you how to convert atmospheres to millimeters of mercury or torr, right underneath the gas constants. And I don't think it tells you how to get to Kelvin. I'm looking, but I don't see it.
Kelvin equals degrees Celsius plus 270.
Where's that?
It's in the gas liquids and stations under the N.
Oh yeah, okay. So yeah, you do have the equation to get to Kelvin on here. So you knowing where things are on this is going to really help you out.
Where's
okay. The what one?
Never mind.
Okay. So we can rearrange that kind of awkward looking equation into what we know as the more readily familiar form of the ideal gas law, PV equals nRT. So in case you need to make a little note to yourself, pressure is going to be in atmospheres, volume will be in liters, and temperature will be in Kelvin. What does N stand for? Moles. Yep. That's the other part of the unit. So N is the moles, not the grams. N is the moles. The ideal gas law is an equation of state for a gas where the state of the gas is its condition at a given time, meaning you're going to have specific pressures, volumes, temperatures, and numbers of moles to fit this particular situation. Okay? So when a gas obeys this equation, it's said to behave ideally. We're going to talk about in 3.6 when they are not ideal. But for now, it's regarded as a limiting law, meaning it expresses the behaviors that real gases approach at low pressures and high temperatures. So gases only behave ideally at these two conditions, very, very low pressures and very, very high temperatures. So this means that, you know, in our room right now, gases are probably not behaving ideally because it's not a low pressure situation and it's not a very high temperature situation. So an ideal gas is pretty much a hypothetical substance that you won't encounter in your everyday life or in your science life either. Okay, so just to practice how to use the PV equals nRT equation, a sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres. Calculate the moles of H2 molecules present in this sample. So it's always good to know what you have and know what you don't have. Okay, so the 1.5 atmospheres will be our pressure. We don't need to convert that because it's already given in atmospheres. The 8.56 is our volume because it's liters. Then 0 degrees Celsius is our temperature, but we need to convert that. So you could just say 273. If you want to be very exact like we were in Chem 1, we did use 273.15. You'll get the same, basically the same answer either way. So if you have that committed to memory and want to use that, that's fine. And then the R value is the constant, so that's the same every time. 0.08206. I'm not going to write the whole unit for that. And then we want to calculate moles, so we want to solve for n. Okay? So we should just plug that in and solve for the answer. So 1.5 times 8.56 equals n times 0.08206 times 273. What do you get? Somebody else get that too? Good job. Okay, now for rounding purposes, 0 degrees Celsius is an absolute number. So we're not going to use the 0 to figure out significant figures. We'll use the rest of the values. So we would go to 2 sig figs because of the 1.5. So that would be 0.57 moles. That's what atmospheres. Okay? Do we remember doing this sort of thing in Chem 1? Possibly? It was chapter 14, in case you were wondering. Okay, so this is just to refresh our memories on how to use the ideal gas law. Are you going to just do this in this class? No, you are not. But we just need to make sure we know how to do it. So what we are going to use the ideal gas law for is many different situations where we can virtually do any problem that deals with gases and apply the ideal gas law to it. The basic assumption we make when using this gas law is to describe a change in state for both a gas that the equation applies equally both to the initial and the final states. So in Chem 1, we had an equation where we had like P1 V1 equals P2 V2. And we had another one that was like V over T equals V over T, where those were initial and final states, and we had specific equations for that. We can apply that same principle with the PV equals nRT, having your initial states and your final states, and still get the same kind of system. Okay? What you do if you have the beginning states and the final states is you just put an equal sign and cancel out the constants. So we'll see how that works. Okay? Suppose we have a sample of ammonia gas with a volume of 7.0 milliliters at a pressure of 1.68 atmospheres. The gas is compressed to a volume of 2.7 milliliters at a constant temperature. Use the ideal gas law to calculate the final pressure. Okay, so we know some information. Okay, where we're going to get rid of constant parts. So we have, the first volume we have is 7.0 milliliters. And we have a pressure of 1.68 atmospheres. Then it says the gas is compressed. So what that is a key for is that the amount of gas particles is not going to change. So which letter do you think remains constant because the amount of gas is staying the same? The volume is going to change because it gives you a different volume. But it's one of the three that we have left. The moles. The moles. So when it says compressed, so it's the same gas that's just getting compressed, the moles is a constant. So I'm just going to put constant for now. Okay? And yes, somebody said temperature. It does say constant temperature. So that means that the temperature doesn't even matter what it is because it's also going to be constant. And what about the R? Is the R going to be constant? Yeah. Yeah, because R is the same every time. So that means that what we can do is if we have our PV equals nRT, everything on this side is constant. So we just get rid of everything that's constant, and then we can form where we have initial pressure and volume, and then we have a final pressure and volume. So it just forms into those equations that we used to just have on an equation sheet. Okay? So now I'm going to just label the two So I'm going to cross these off because they're constant. And I'm going to label the 1.68 atmospheres and the 7.0 milliliters as initials or ones. So then the other volume, the 2.7, is going to be a second volume. So that'll be V2.
But don't we have to change it to
You could, but since we've changed our equation and we're not using the R value, we can leave it as milliliters. You should get the same answer either way, but it would just be a little bit more work to do that. So then now we want to know the final pressure, which would be the V2, or sorry, the P2, and so then we can use this to solve. Now, so we would have 1.68 times 7 is equal to P2 times 2.7. Maybe we get the answer? 4.4? 4.36, so two significant figures, 4.4 atmospheres. And remember, the pressure unit, you just look at what the other one was. So there we go. Now, this one, it works out that our constants were all just on the same side of the equal sign together already. But you could do the same principle if maybe the constants were like pressure moles and just like pressure in moles. Then you could divide the pressure over, and you could divide the temperature over to get all the constants on one side. So that's mainly what you have to do, is just reevaluate the equation to get all the constant variables on one side, and then the not constants on the other side, and it makes the equation that you need. Okay? But that's one way we can apply it. Another way that we can apply it with this whole idea of initial and final is maybe we have two sets of conditions, and we need to find both of the new conditions and then go from there. So that's what example 3 does, where, ooh, I had a lot more space to work on. Good to know. A sample containing 0.35 moles of argon gas at a temperature of 13 degrees Celsius and a pressure of 568 torr is heated to 56 degrees Celsius and a pressure of 897 torr. By the way, I forgot to say this. Torr, the unit torr is equal to the millimeters of mercury unit, which you can see that on your equation sheet. The reason why they have torr is because the guy who measured with millimeters of mercury, his last name was Torricelli. So it's just like a nod to him to have a unit named torr. So we want to calculate the change in volume that occurs. So we have moles, which is our N, right? And we have a temperature and a pressure. And then we have another temperature, another pressure, and we want to calculate the change in volume. This time, how would you find the change in volume, by the way? What would you do to find the change in volume? If we had an initial volume and a final volume, what would you do? Subtract them. So eventually we're going to have to find the change in volume, we'll have to take the final volume minus the initial volume. Okay? So we are going to need to solve for each of the volumes separately, so then we can then take the difference of them. Okay? On this one, what I did is I solved two separate equations, plugging in my two conditions to get the two different volumes, and then subtract at the very end. Okay? Let me just see if I have more space. Oh, look, I do. Okay, so my initial conditions, I labeled the first numbers as initial conditions. So we had 568 torr, and the volume is what we're solving for, and we have 0.35 moles, and we have 13 degrees Celsius. So we have to change our Celsius, and we actually have to change our torr as well. Okay, and then we're going to have to do the same thing for the other set of conditions, where P2 is the 897 torr. We're solving for V2, and N2. What do you think N2 is? Do you think do you think the moles change, or do you think the moles are constant this time? They're constant. So the moles is the same 0.35. The only two things that are constant this time are N and R, so that's why I did it this way. Okay, so to add 273 to 13, you get 286 Kelvin. And then add 273 to 56 and you get 329 Kelvin. Okay. So now on your equation sheet, it tells you that 1 atmosphere is equal to 760 millimeters of mercury or 760 torr. So how are we going to get this to turn into atmospheres? Do you multiply or divide to get it to change to torr? I mean to atmospheres. Divide. Yep. So we need to divide this by 760 each time. And I don't have these numbers written down, so I'll have to have somebody tell me that. 1.18. Okay. So can I have one person solve the ones equation and one person solve the twos equation to speed up the process? Is it okay if I don't like show it written out in its equation form? Do we all know what we're doing there? Okay.
So first one I got
952. Okay. Did you get that? What did you get?
I got 10.22997. I did the math wrong.
229? 10.229? I got 10.66.
I got whoa. Second one I got 8.01.
I got that one on the second one.
The first one I didn't even get 10. What'd you get?
Oh wait, I divided it backwards.
0.35. 9.3 times.
I got 10.952.
Okay, 10.952. That's fine. Yep. I think mine was a little bit more accurate because I used the 0.15 with mine. So that's fine. Okay, so then we now have our two separate volumes, but we need the change in volume. And so it's always change in volume. It's always final minus initial. So even though our final is bigger or smaller, it's okay because we want to know the change. So the change is going to be 8.01 minus 10.952, which is and let's round it to two significant figures, negative 2.9 liters. Does anyone else get that? Okay. So, those are just two other ways that we could use the ideal gas law, and you might have to use it twice in the same equation. You just have to make sure, the hard part is organizing your data. Make sure that you get all of the initial conditions together and all of the final conditions together. Okay, that's a difficult part of that. So, moving forward, what if we had 1 mole of an ideal gas at 0 degrees Celsius in 1 atmosphere? If we plug that into the equation to solve for volume, we have 1 mole times R. I'm just trying to prove something here. Times 273 you would get that the volume is 22.4. Does anybody remember what that's called? It's right underneath it. The 22.4 is called molar volume. It doesn't matter. I don't care. I was just proving it to you. So now 22.4 is kind of rounded because different gases have more exact molar volumes, and it might be a little bit different because the amount of it could be for lots of different reasons, but in general we just say that 22.4 liters is the molar volume. And does anybody remember the 0 degrees Celsius in 1 atmosphere? What's that called? STP, standard temperature and pressure. Yep. So these are common reference conditions where instead of giving you 0 degrees Celsius in 1 atmosphere, it might just say at STP. And so you're going to have to remember that. But it's on the equation sheet for you. So you can help yourself that way.
You can use that for
Yes. Yep. So this is just a problem where you would have to solve where it gives you the words STP. Do we feel like we need to solve that, or do we feel like we're okay? We can do it? Okay. Yep. So a sample of nitrogen gas has a volume of 1.75 at STP. How many moles are present? So we're still using our equation. We only have one pressure, one volume this time, so we know we don't have to do it twice. And we know that the volume is 1.75 liters. And we're solving for moles, which is the N. Now, at this point, we know R can be filled in, but we're still missing the temperature and the pressure. And so that's where, like, your hint of STP tells you you have to plug in 1 atmosphere and then the 0 degrees Celsius or 273 Kelvin. Okay, so if it ever just says STP, then you automatically plug in those values. And so it'll be 1 times 1.75 equals N times R times 273. And again, so STP values are like absolute values. So we're not going to use the 1 ATM or the 0 degrees Celsius or the 273 to worry about for rounding. We would look back at the 1.75 to round to 3 sig figs. So I got 0.0781. Is that what you got too? Or close to it? We're tracking our way.
What do we end?
The big one.
All the notes?
No, we're not doing all of it. We're going to end after page 12.
Which one's? Oh, man.
We're on page 10.
Oh, we're doing all of 3.4. I thought you were doing
Yes.
all of 3.4.
No, we're doing all of 3.4. No.
Can we spell it?
No. The calendar doesn't say that. We can do that. And we also have to talk about something else in the videos. Okay. Example 5. A sample of methane gas is having a volume of 2.80 liters at 25 degrees Celsius and 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35.0 liters at 31 degrees Celsius and 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. Create the volume of CO2 formed at a pressure of 2.50 atmospheres and 125 degrees Celsius.
That's a lot of
What?
words.
It is a lot of words. Okay, so hint. You ready? We have information about methane gas, which in the EP exam it would say CH4, and I just didn't include that, so it would be there for you. You wouldn't have to necessarily know what methane was. But it's mixed with oxygen gas, which is O2. And then ignited. What do you think ignited means?
It's on fire.
It's on fire, and fire is a type of
Reaction.
reaction. Yeah, chemical reaction. So if this is mixed with this, ignited to form,
We have to make our. Oh my gosh,
it's a combustion reaction.
Wow.
What? So we can use the PV equals nRT with a stoichiometry problem. Oh yeah. Okay, so I have space over here. So let's just write out and balance this equation first. So we have CH4 plus O2, and it forms CO2 is carbon dioxide plus water is H2O, not OH2. Or not HO2. Okay, so is it a balanced equation? We always have to think about, is it a balanced equation? No, it's not. So how would we balance it?
2 in front of the O2 and 2 in front of the
Yep, 2 and 2. Okay. So now, what I'm going to do this time is I'm going to list underneath, just like I do when I'm doing like stoichiometry with a mole map problem, I will list what I know about each type of gas underneath. Okay? So the methane has a volume of that at this temperature and this pressure. So I'm going to list all that stuff under the CH4. So I know that the pressure is 1.65 atmospheres. I know that the volume is 2.80 liters. And I know that the temp was 25 degrees Celsius. There. We'll probably have to change that Celsius, but we'll do it in a second. Okay. Then, the next set of numbers we have for oxygen, so this is oxygen gas, has a volume of 35 liters at 31 degrees Celsius and that pressure, 1.25 atmospheres. So under the oxygen, I know that the pressure is 1.25 atmospheres. I know that the volume is 35.0 liters. And I know that the temperature is 31 degrees Celsius. But there's still more numbers. Oh wait, but there's more. So we also know that we know the pressure and the temperature of the CO2. So under the CO2, I know that the volume is 2.5 atmospheres, sorry, and that's pressure. And then the temperature was 25 degrees Celsius? 125, thank you. I didn't write down the Celsius, I just converted it automatically on mine. Okay, and what's the question asking for? The volume of the CO2. So at the very end of the problem, we want to know the volume of the CO2. Anybody want to take a guess at what we're going to do here? Jojo, are you like mentally breaking down right now?
Yes.
It'll be okay.
You do.
What are we going to do?
Do your
Magic.
You do like
Do
the thing
magic.
that you do when you like
Do you
the
add
thing.
the stuff on the left together and then like
Well, if it's chemical reaction, we can't just add them all together because there's not the same kind.
like on the left side of the arrow? Mine's a mess because it was multiple.
What do you think, if we plugged in this information into the equation, what do you think we would solve for?
Moles.
Oh, both of
Moles.
Oh, you solve for moles and then you can solve for CO2. Is that
So,
right?
yeah, so we would have, if we plugged in this information, we would be able to solve for moles of each of these things. Okay? And does anybody remember, what do we call it when you have a chemical reaction and you're given information about both reactants? And then we have to only solve for one answer at the end? Yes. This is a limiting reactant problem.
Different problems are in this
I don't know if I have
problem.
enough space.
I know, right? Look at mine. It's all over the place. So, this is a limiting reactant problem. So maybe you like make a little note to yourself. I know now for next year to give you a whole entire page to solve this problem.
Has she? Wait,
More than half a sheet of paper. Okay, so what we're going to do is we are going to solve for moles of CH4. We're going to solve for moles of O2. Then, what do you do when you know the moles of each of the reactants?
Is it like the round by the little fry part? The little round.
We're not going to do the rhyme. No, we have to turn it into moles of the product that we want.
Moles.
Moles 1 over moles half multiplied by a mole ratio. And then the smaller of the two numbers is the one that we use to get to the final answer. So when we convert it to moles of CO2, then the smaller of those two will plug in here and then solve for volume of that.
I think we should just take a break. I can't do this.
I think we're good.
Oh my gosh.
We might have to break this up over 2 days. So we only have 15 minutes left. We got this.
The
We got
calendar
this.
won't let us.
The calendar won't let us.
Good thing you said
Okay,
no.
here we go. Ready? This is CH4. CH4, ready? We have 1.65 times 2.80 equals N. To save some space, now I don't want you to like get confused. If you feel like you need to do this, do it. But to save space for me, I know what R is, so I'm just going to put the letter R on my paper. And then this will be 298 Kelvin. So just to save space, I wrote R. But you know what R is because R is 0.08206. Okay? And I'm going to put moles of CH4. Because if we have N's all over the place, you have to know what the N stand for. So this moles that we're solving for is for the moles of CH4. Okay? And then we're going to do the same thing with the information for the O2. So for the O2, this is CH4, we have 1.25 times 35.0 equals N times R times 31 turned to Kelvin is 304. So this I'm going to relabel as moles of O2.
The first one is 0.89.
I got 0. I got 0.11332.
Oh my god, 0.18. Yeah.
0.189 is correct.
Yeah.
Are you making sure? Are you putting like 0.8206?
0.0820. I did not take that as a calculator.
Yeah.
Like I used the exact.
Oh, the exact numbers. It should be fine. I use exact numbers too, but
Second one's 1.75. Is that right?
yep. You got this. You got this. Okay, so now this is moles of CH4 and this is moles of O2. Now we're going to multiply to change it into moles of what we want, which is the CO2. Because what we want to know about at the end is something about CO2. So we're going to multiply by the mole ratio. So I'm going to just add, just to help you, those CH4 and O2. Now, mole ratio. What goes on top? How many moles of CO2 do we have? What's the coefficient in front of CO2? 1, right here. This is a 1. So it's going to be 1 mole of CO2 over what's in front of CH4? A 1. So that means that from the CH4 data, it gives us 0.189 moles of CO2. We have to compare that to the moles of O2. So for the O2 mole ratio, it's still going to be 1 mole of CO2 in the numerator, but this time we have a 2, so we have to divide it by 2. So what do we get? 1.75 divided by 2, 876. Okay, we're almost there. We're almost there. We are no longer going to be doing 2 sets of solving because now we have to make a choice. Which are we going to choose? The 0.189 or the 0.876? The lowest of the 2. So this is going to be the moles that we use here to then solve for volume of CO2. So now we're done with this, and now we're just using this. Are you still thinking about it? Okay.
How much is the
So for the CO2, we would have the 2.5 atmospheres times V equals 189, sorry, times R times 398 Kelvin. And that volume is 2.5 liters. Somebody else get that? Okay. Does anybody need more pointing or explaining?
No, I'm just working.
Okay.
where's the 398 from?
This plus 273. You'll probably get committed to memory pretty quickly that 25 degrees Celsius is 298 Kelvin, because it's just something that's used a lot. So then, yeah, you might just get that quickly added to your brain for
Good
knowledge.
everybody. You did a good job today.
Oh, still, it's really
Yeah, like I'm going to join a part class after this.
It's just a lot of work. What? Maybe.
Can I just be the only question?
No. Can I tell you, we're only halfway through 3.4 right now.
I had to switch to pencil because I couldn't understand my pen any longer.
Can you keep us for 6 hours?
Yeah.
No.
No, I need to work today. Is it a weekend?
Riley, is it okay if I
Yeah, you
cut it?
You don't have